Austin. He's going to tell us about the mirror symmetry, partition functions, and gauged linear Quivers.
Well, thanks very much for the invitation. It's a real pleasure to be back at ANN. The main player being cast today's talk would be n equals to 4 3D Suzy gauge theories. So let me begin by saying a few fundamental things about theories in this category. So n equals to 4 theories in 3D have 8 real supercharges, which are doublets of SO2R. And transform as a 2, 2 under the n equals to 4R symmetry, which I'll label as a product of SU2L and SU2R. Now the super multiplets of n equals to 4 that we'll be concerned with are the n equals to 4 vector multiplet, which has the following transformation property under the R symmetry. So the first parenthesis indicates bosons, the second one fermions, and n equals to 4 half hypers. Which transform as a 1, 2. Again, bosons, fermions. So when people say n equals to 4 hyper, what they mean are 2 copies of these half hypers. Now, n equals to 4 theories that I'm going to talk about will be classically non-conformal, but in the IR, they'll approach a super-conformal fixed point. So in the IR, it's 3 to infinity. These approach SCFTs. The low energy theory of this category has 2 distinguished branches, namely the Coulomb branch and the Higgs branch. So the Coulomb branch is where the gauge group breaks into the maximal torus. It's parametrized by the 4 scalars, 3 adjoint scalars in n equals to 4 vector multiplet, and the 1 dual scalar, dual to the gauge field. So it's a hyperkähler manifold. Labeled by vector multiplet scalars.
By maximal torus, you mean the Cartan subalgebra?
Yeah, the U1.
Okay.
Yeah, the U1 branch.
Yeah.
While the Higgs branch, on the Higgs branch, G is generically broken completely. And this branch is, again, a hyperkähler manifold that's parametrized by the hyperscalars.
When you say generically completely, do you mean it doesn't have to be completely broken?
There are some cases, some special cases, where it's not completely broken. So this is the thing about the Kibble branch versus the Higgs branch thing. So there are some cases, that's why I'm using that word generically.
Okay.
But for most cases, and in the cases that I'll talk about, it's completely broken.
Okay.
Yeah.
What were the 4 scalars in the Coulomb branch?
And the Coulomb branch?
Yeah.
So the 3 from the adjoint n equals to 4. So n equals to 4 has like n equals to 2 vector plus 1 n equals to 2 chiral. So 2 come from there, 1 comes from the n equals to 2 vector, that's 3, and the other one is a dualized scale.
Okay.
Now, okay, I should probably mention that this dualization actually just works in abelian theories. But I'll be talking about the Coulomb branch, where the gauge group is broken to U1 to the power rank G. So it's essentially a set of abelian theories. So that's why it's useful to carry on the counting like this.
Can you briefly comment on in the parentheses the historic origin of the terminology of Coulomb and Higgs?
I guess
Why are they
Coulomb
called
is
like
just
that?
U1, so that's why I think it's called Coulomb.
Oh, because it's U1.
Yeah, and like Higgs, completely broken, I guess. That's why Higgs. I don't know.
In Coulomb branch, the gauge group is broken. Do you want due to what mechanism?
I think that's Higgs.
Still Higgs,
Yeah.
same as Higgs branch.
Yeah, but it's completely, so it's like
Okay.
complete
I
Higgsing.
see.
So,
Okay.
so that's why I don't know. Maybe it's something different. That's my guess. Yes, that's important actually. So in both cases, it's actually Higgs mechanism. So,
May I ask one question about the Higgs mechanism? So say, we know that for the Higgs mechanism, when the symmetry is broken, we need to write the scalar potential as 5 bar minus something on squared, right? That's the general Higgs potential to break the gauge symmetry.
right.
And in that case, actually, it is not homomorphic. It is not the product of the homomorphic part and the anti-homomorphic part.
I don't understand.
Then, okay.
In which context are you talking about Higgs mechanism? In which context?
I mean, in the frame to discuss about the Higgs mechanism.
That's like it's actually a small detail. So let me proceed,
Okay,
and we can probably talk about that once. So that's the low energy theory. Now you know that because of this parametrization by scalars, there is a natural action of SU2L on the Coulomb branch, and the natural action of SU2R on the Higgs branch. Okay, so these are often referred to as SU2 Coulomb and SU2 Higgs because of this thing. Now, in addition, one may turn on background okay, I should mention one thing. So in addition to these, so you see that these multiplets are not symmetric under the action of SU2L and SU2R, right? So there's an asymmetry in the action. So just like we have vector multiplets and half hypers, we can have twisted vector multiplets and twisted half hypers, okay, where just the action of SU2L and SU2R are reversed. Okay, so one can have twisted multiplets as well. So in addition to the ones that we stated, there could be background vector or twisted vector multiplets. And these appear in the UV theory as masses, hypers, and Fi parameters, respectively. So that pretty much is the low energy description of n equals to 4 3D theories. That's all you basically need to write down a Lagrangian description. Now, n equals to 4 theories are known to have some really interesting IR dualities. And one of the classic ones in this category of dualities is what is known as mirror symmetry.
Is this a quantum symmetry?
It's a quantum symmetry, yeah, absolutely. I mean, that's why it's actually useful.
Yes, yes.
Right. So what it does is that you start with two theories which have completely different UV description, and they flow to the same superconformal point in the IR. So the IR, theory A and B, flow to the same SCFT, such that in the low energy theory, the Coulomb and the Higgs branches are interchanged.
You mean low energy description at IR, you mean?
Yeah. Sorry. So if you look at the low energy theory of these two theories which have completely different UV description, you see that the Higgs branch of one is the Coulomb branch of the other, and likewise. So what does this mean? So the first thing that this means is that the action of SU2L and SU2R are reversed. So first thing is SU2R, SU2L. These two actions are reversed, which means, yeah, go on.
So what is this a symmetry of? Because it's a relation between two different theories, right?
Yeah, it should be probably better called mirror duality.
Okay.
Yeah, symmetry is but historical reasons.
Okay.
Which is self-duality.
The what?
Are some
Function
theories,
is self-duality series.
are some theories self?
Self, yes, there's some, yeah, like you want with two flavors, for example, it's self-dual. There are a bunch of examples.
Yeah.
But those were not the ones that were first discovered, so I don't think even that was historically the reason. Anyway, so this is the first thing that happens, which automatically means an exchange of the background vector multiplier and the twisted vector multiplier, right? Which would mean that the masses and the Fi parameters are also exchanged. Okay. So this is kind of the hallmark of mirror symmetry, that the masses on one side kind of become Fi parameters on the other side. Now, in most theories, this is not a simple exchange. There is actually a linear map that connects masses on one side to Fi parameters on the other side and vice versa. And this is usually called the mirror map. So given a pair of mirror theories, one of the first things that you want to know is the mirror map, as to how the masses on one side basically map the Fi parameters on the other side. Another set of information that you might want to know is how chiral operators on one side basically map to chiral operators on the other side. But this is kind of the first elementary set of information that you want to know. So note that this is actually a quantum duality, because the Coulomb branch of an n equals to 4 theory is highly quantum corrected. On the other hand, the Higgs branch is exact, right? So if you exchange Coulomb and Higgs branch, you are basically having a classical result on one side, Higgs branch on one side, but that corresponds to the quantum result on the other side. So the Coulomb branch of theory A is quantum corrected. The Higgs branch of theory B is not. It's a classical result. So you're basically computing a classical result, but that's actually a quantum result for a different theory. So that's why it's kind of useful. And it's actually a duality that involves strong computing. Sorry, that involves quantum corrections.
So there's some non-normalization theorem in the Higgs branch. Is that what you're
That's
saying?
right, yes. For n equals to 4.
Mm-hmm. Okay.
Yes. I mean, you can also see it from the point of view of background hypermultiplets, basically. So the masses and the G Young-Mills, they basically belong to the same background hypermultiplet. So you know that the Coulomb branch will be corrected by the masses, and so that's why the G Young-Mills is also there. Now, when the masses are not there, the G Young-Mills are also not there. All right. So
This theory perturbative or non-perturbative? This theory is perturbative or non-perturbative?
I mean, they have UV descriptions. So there is a Lagrangian for most of them. But the IR limit is not. Yeah. Again, there are exceptions, but mostly, generically, they're not. But that will not matter for a reason that I'll explain in a second. So just to complete the n equals to 4 story, so these theories can be realized as word volume theories on D3 rings type 2B theory on R2, 1 cross L. We call this R3x, Y. So the G3 wraps this R2, 1 product with this compact reaction L. Okay, and what you have are half BPS boundary conditions at the two ends of L. This is the classic Hanani-Witten or Kyoto-Witten story. Okay, so the total data consists of this geometry and half BPS boundary conditions at the two ends, and that gives you your expected n equals to 4, 3, and 3. Now for mirror symmetry, there is a very nice interpretation from type 2b, and namely that is mirror symmetry is exactly equivalent to S duality in type 2. What this means is the following. You start with a bunch of D3 branes with certain half BPS boundary conditions at both ends. That could be anything, need not be branes or just any generic half BPS boundary conditions, as long as you know how to evaluate the low energy theory. And then that gives you one quiver gauge theory. And then you can S-dualize it, so the half BPS boundary conditions become something else, and you can reevaluate the theory. And these two theories are mirror symmetric to each other. So for example, if you have quiver theories of the A type or the affine A type, the only kind of half BPS boundary conditions that enter in the fray are NS5 and D5 branes, which are S-dual to each other. If you further venture to D-type, affine D-type quivers, then in addition to the NS5 and D5, you'll have other objects like orbifold 5 planes. Which are S-dual to what are known as the O5 zero planes, which is a coincident O5 minus and a D5. So these are examples of objects that you can have in various theories. But the basic idea is very simple. You start with a scenario, take the S-dual, and you have mirror symmetry, mirror dual theories on both sides. Now for affine quiver gauge theories, that which kind of will be the main topic of this talk, there's also a very nice description from M theory. So what you do is you start. Okay, are there any questions until this point?
Yeah,
sure.
I'm a bit confused because I thought symmetry is usually T-duality along all torus vibrations. I mean, kind of T-duality along all torus vibrations.
In what?
If you have a compactification on a Calabi-Yau.
No, that's a different mirror symmetry. I mean, are you talking about the homological mirror symmetry? Like the
Yeah, well, Calabi-Yau mirror symmetry. So it's not.
Storm don't go on such mode.
Oh, okay. No, but this is slightly different, I think. I don't
So
know
it's
if
really
there's-
something completely different.
Yeah, I mean, I have seen papers on geometric engineering which kind of try to relate the two in some cases, but I don't think they're generally complete. In any case, if you state it in this way, then there is no connection between the two. But I'm not saying that they're completely unrelated. I don't know. That's something that it's the same case with the 2D mirror symmetry too. There are some cases that you think that there's a relation, but generically there's no relation. But if you take it this way, then as you can see, there's no reason to get into that description. Yes?
Can you derive these quiver theories, strictly speaking, by starting from a Green-Schwarz type action for these three branes that you all know, and then plug in the background you're interested in? Or is it just an expectation? You say it's a wall volume theory on D3 branes, you say, in your first line, in that comment.
Right.
but is that actually doable in practice?
Yeah,
Can
yeah,
you
yeah.
start as people obtain the quiver theories from D3 brain action?
Isn't it the alpha prime to zero limit?
Yeah.
The D3 brain work volume theory.
Yeah, that's right.
Oh, alpha prime goes to zero limit you want, low
Yeah.
energy description.
That's right. So,
Well, it makes life easier, I would say, in some sense. So is it doable? Or just an expectation, what you're saying?
well, no, I would think that, yeah, I mean, so this was done in the mid-90s. I mean,
Mhm.
I would think that people have actually done the Kaluza-Klein reduction, and that's what you're saying, right?
No, Green-Schwarz string, D-brain I'm talking
Is there
about.
now
But you have to reduce on the L, right? I mean,
Okay,
Is that what-
Green-Schwarz is only known for a billion, that's true.
Yeah, that's another
Born type action. So then, in practice, you have to assume some non-abelian version of sort.
well, maybe it's you can do it separately on the Coulomb branch, like
Yeah.
it's there you have a product of U1s and then probably you can do something. I'm not familiar with the exact computation on that,
Okay,
but yeah.
okay, thank you.
Okay, so let me quickly state the M theory description. So you consider a stack of M2 brains. On a geometry, which is a product of two ALE spaces. Okay. And then what you can do is that you can deform first ALE to an ALF. And you can do the same thing with the other ALE. Okay, so there's the two different ways in which you can deform this geometry. And this, in the type 2A, becomes a set of D2 brains with D6s wrapping ALE2, and on this side, this becomes another set of D2 brains wrapping ALE1. Sorry, with D6 wrapping ALE1. So what you can do is that you can, from this description, you can quadratically calculate what is the word volume theory on D2 brains on both sides. Okay. And in the IR limit, they both go back to this solution of M theory. Okay. So that's mirror symmetry. So in the IR, they basically have the same description, which is given by this geometry. Okay, but so what more can we say about this? Now it turns out that so this was all discovered kind of in the mid-90s, and beyond the very simple abelian theories, not much could be said until we finally ended up with a strong tool of localization, and that's when it became even more interesting to study these theories and actually probe the duality in some more detail. So right, so let me let me very briefly state the results of localization that I'm going to use in the next few minutes. So as you know, the basic idea of localization is the following, is that you can compute exact RG independent objects and this is really useful for theories, this is really useful for IR dualities, because you can compute these objects from the UV descriptions, and then they must agree in the IR. So that's an immediate test for things like mirror symmetry. So the particular observable that we are going to use today, to some degree, is the S3 partition function. Okay. And for a generic n equals to 4 Quiver gauge theory in 3D, the localization of the result of S3 partition function due to bilocalization was done by Kapustin and collaborators. And I'm gonna quickly state the results. So a generic partition function assumes the following form after localization. I'll explain the symbols in a second. So it turns out that the partition function reduces to a matrix integral over the adjoint scalar in the n equals to 2 vector multiplet. I denote that as S. And furthermore, you can do a constant gauge transformation, which maps S to the Cartan of the gauge tree. So it's basically a matrix integral over just the Cartan. So this W is the order of the while group, and this product is over all roots of G, just the van der Waals determinant. And then you have a classical contribution and a one loop contribution. So what remains to be stated is that how the different multiplets, namely hypermultiplets and the vector multiplets, how they contribute to each of these factors. Right? I'm going to be So the vector multiplet contributes an Fi term for each U1 factor in the gauge group. And to the one loop action, it contributes the following product of overall alphas, sine hyperbolic squared pi s. The hypermultiplet contributes nothing to the classical action. Contributes to the row. Rho S plus F. So this is a product over all roots. This is a product over all weights of the corresponding representation in which the hypermultiplet transforms. Okay, so if it's R, then rho belongs to R. The representation R. Okay, so in the simple cases, for example, if G were a UN, this product over alpha sine hyperbolic squared pi alpha s would be simply I less than j sine hyperbolic squared pi si minus a sj, where I and j run from 1 to n for un.
What's the symbol in the argument of the Koch, right? Symbol.
This one?
Yeah.
This is a row, the weight. This one?
Yeah.
Pi.
Thanks.
Oops.
I have technical question.
Say what?
I have technical question.
Okay.
Technical question.
Yeah, sure.
To do this localization, you need to go to the reading signature.
Yeah. SP, yeah.
Then in that case, do you worry about supersymmetry breaking or?
No. So you basically compute the killing spinors on S3 or whatever
S3.
on whatever free space that is your favorite.
And the signature couldn't change the supersymmetry.
Yes. So you deform the supersymmetry. Yes. Yes. But that's, I mean, so there are some results that you think you cannot capture. That, like, if you're trying to study instant downs in R2,1, then that won't be visible in this. Okay? There are no instant downs on S3. But the one loop part, that you expect to be the same.
Just answered my question.
Okay.
So the instantons would have been like monopole.
Yes.
and
That
they
you
don't
can
exist on
Yeah,
this.
yeah. I mean, that's the difference with S4. Okay. So, and for example, if you have fundamental hypers, for example, okay, their contribution would be, so this product of rho, 1 over cosine hyperbolic phi, plus m, would simply be product over all I, cosine hyperbolic phi, si plus n. Okay. So the weights are just S1, S2, S3, and so on. So now if you see that, you know, if I have n masses, for example, and the structure is such that this that is such that, you know, you can totally see that whatever this whatever this you know, this particular fundamental hyper is actually in the fundamental of the gauge group and the bifundamental. Fundamental of the gauge group. Let me see. You can see that the hypermultiplet is a bifundamental with the two groups. One of them is the gauge group, the other one is a plate group. Okay, the structure is exactly that. It's like Si minus Sj. So so if you have n hypers, in a gauge group G, you can represent it this way. It just means that there's a cartan of G, there's a cartan of, you know, for Un, is charged in this way, of which only G cartan is G. So you have an integration over S and not over N. But the structure is indeed that of a bifundamental. But we're going to use this fact to our advantage in a few minutes. Okay, any questions to this point? This is like still you know, setting up. Okay, very good. So let me repeat what I've done. So I started by defining what n equals to 4 theories in 3D are, and, you know, what are the fundamental you know, information about the low energy theory that you could be interested in. And then I also described the possible type 2b descriptions of such theories, and told you what mirror symmetry could be, how mirror symmetry could be interpreted in terms of those things. And then what I've done here is just to write down for a generic n equals to 4 supersymmetry gauge theory the prescription for writing a partition function on S3. Okay. So now, if I have a mirror pair, what I can do is that I can compute the S3 partition function of theory A on one side, S3 of theory A on one side as a function of masses and Fi parameters. And I can also do the same for theory B, again, as a function of masses and Fi parameters. Okay. And if they are indeed mirror dual, then they should be equal to each other, provided the masses, MAs, are related in some way to the Fi parameters on the other side. And the Fi parameters on side A should be related to the masses on the other side by a linear map. So both F and G should be linear maps.
So do you know a priori which kind of linear map do you have?
No, that changes from one set of theories to another.
It depends on something.
It depends on the theory. What? Yeah. So I mean, there's a generic form for, I mean, the category of theory that you're probably talking, like, you know, D-type, affine D-type theory is in a certain form, affine D-type theory. So.
how does the S3 in the two branches, are they same or have different radius?
Say again.
I mean, how does they, you have two S3 in two different branches, right?
S3 in
S3, I mean, the S3 sphere.
Yeah, in what?
And are there any relationships between the two S3 when you dual the two branches?
I mean the Coulomb and the Higgs branch?
Yeah.
This does not really depend on that. I mean,
Independent of the size of
yeah, this does not depend on which branch you're really talking about. I mean, the final result is like that's that information of the IRSCFT. But the localization that we do, that localization is indeed done on the Coulomb branch, but that does not affect the result. I mean, it's an observable of the IRSCFT itself. Right. Was that your question or? Yeah.
Yes.
Maybe a related question is, do you do the localization of theory A and B on exactly the same three-sphere, or is there a relationship?
Yeah, because there's a mirror symmetry, so maybe the two spheres.
No, I mean it's just three sphere is just labeled by its radius, right?
Right, so it's the same radius?
Yeah, just say the radius to 1 in both cases or something. Yeah, so because otherwise, it has to be on the same manifold.
Well, I don't know. A priori, it could have been.
No, but then there's the duality is hard to establish, right?
You haven't considered the mirror symmetry, including the change of the radius.
Yes.
Yeah. Maybe inversely.
No, but the two theories must live on the same three manifold, right?
Yeah, I mean.
Possibly, right? I mean, because otherwise, I can. Okay, so I think we are all set to begin the main thing. Which is okay. Any other questions before I? So the new thing that I plan to talk about. So this is work done in collaboration with Ami Hanani, Peter Korotev, and Fadil Mikaria. Which basically says the following, is that you can generate a wide class of mirror dual theories from mirror pairs which are exclusively linear with unitary gauge groups. Okay, and the way you go from here to here is by gauging certain flavor symmetries. Okay, so let me state what. Well, maybe let me begin with an example. So.
Is that error meant to indicate RG flow?
No. Just. So let's start with a simple example. Quiver of this form. Which is mirror dual to this quiver. So let me explain what this symbol means. So the circles with the numbers in them mean UN gauge groups. So the number within the circle means the n of UN. So this, for example, is a U1 cross U2 cross U1. And the lines connecting the circles are bifundamentals in their gauge groups. Okay. So you have one bifundamental of U1 cross U2 and another bifundamental of U2 cross U1. And boxes mean fundamental hypers, which basically, and this means that it's in the bifundamental of U2 and the U2 flavor group. So here also it's a bifundamental, but of the two groups, only one is gauged. Okay. So boxes mean in general global symmetries, and circles mean gauge symmetries. And this is dual, mirror symmetric to this. Okay. Now, yeah.
Stupid question. Can you remind what does it mean linear?
Oh, linear means the linear chain of nodes. Yeah. So the gauge nodes.
The gauge nodes are
Yeah. They're a single chain, as opposed to say a circle or having tails at the end. Okay, so this you can derive by this type 2B picture, the Hanani-Witten picture, directly. So typically, the positions of the NS5 branes I probably did describe them. Well, I probably wrote down here. So yeah. So these are like the AN type. You know, that's the linear. So the positions of the NS5 branes are usually associated with Fi parameters, and the positions of D5 branes are associated with the masses of the hypermultiplets. So anyway, so from Hanani-Witten picture, you can see that there is a direct map of parameters on both sides. So if I label the Fi parameters in the following way, okay, then these are exactly equal to the masses on this side, M1, capital M1, M2, 3, 4. And the masses here, we call them M1 and M2, and they are equal to the Fi parameters here. So there's a nice map between the two. Okay, so whenever there's a linear map, whenever there's a linear quiver, a mirror symmetry between linear quiver, the masses and the Fi parameters simply get interchanged. So the linear map is a really trivial one. Okay, so masses become Fi parameters and vice versa. And the reason is that in type 2B picture involving these quivers, you only have NS5 and D5 branes. That's all you have. Under S duality, NS5 becomes D5, D5 becomes NS5. So the masses and Fi parameters are just interchanged. Okay. So that's why it's always kind of simple to start with these kind of stuff. But now what you can do is you can gauge this flavor symmetry U2 to a U1 gauge. The question is, what happens on the other side? I mean, it's kind of trivial that you can get this quiver from this. That's not a profound thing to say. But what happens on the other side? Now, what happens on the other side is that the U2 gets replaced by an SU2 or an SP1. Okay. So once you gauge on this side, on the mirror side, this is followed by a related ungauging. So I'm using this word ungauging in a loose way. I'm just using it to mean that the rank of the gauge group on the dual side is decreasing. So as I write down more examples, we'll see that the dual quiver is changed in various ways. But the common feature in all those changes is that the rank, overall rank of the gauge group always decreases. So a gauging on one side of the duality basically means ungauging on the other side of the duality. Now this is made manifest by the partial function computation, although I don't have time to basically write down formulas. But what you can do is that you have certain parameters like m, masses floating around, which transform into fundamentals of the flavor group. Okay. Now you can choose to gauge one or all of them And that basically, at the partition function level, gauges a certain subgroup of your flavor group. Okay? So let me write down the kind of generic formula at least. So suppose, this is the basic idea of gauging a flavor node. So you have a long quiver that does different things, but you have one node with flavor M1. Okay. Now you pick a subgroup M0 in the flavor group, and suppose I choose to gauge that. Okay, so as a result, I will get zero. M1 minus M0.
This process change the degree freedom of the theory?
Yes, surely. As you can see that even the dimension of the Higgs and the Coulomb branches have changed. So I indeed go from a different theory by doing this. But I'm doing all this at the level of the quiver. So now how do I make such a change at the level of the partition function, which is what we want to do? So Z gauge is integral I equals to 1 to M0 dmi M0 factorial, then the van der Waals determinant for mi. Okay, so this is again the product over all alphas that's sitting here. Times the integrand for UM0 vector multiplet parameterized by the mi's in the Cartan. Okay. So I goes from 1 to M0. Okay. And then you have possibly other terms depending on whether you're just gauging or putting other stuff. But let's just this Cm for the time being times the linear partition function that you had, which was a function of mi's m0 plus 1, so on and so forth until m1, and other masses and effect parameters. Okay, so all I have done is I've multiplied a contribution of a UM0 vector multiplet, and I've integrated over volume factor. So this is like the prescription for any quiver gauge theory. If you want to gauge a subgroup of the flavor symmetry group, this is what you do. Does it make sense, or not really? So I'm just replicating what I did here. So you had a partition function to begin with, which was a function of all the masses and Fi parameters, which included this M1 Fi M1 masses, right? Now I'm integrating over M0 of them in a way that this UM0 is a subgroup. So that this UM0 subgroup of this UM1 is actually gauged in the final expression. That's all I'm doing. So having done that, for example, in this case, you can totally see how this SP1 arises out of U2. So in this case, it's kind of simple. You just get a delta function connecting the two entries in the Cartan. Okay, so U2 has diagonal M1 and M2. And so if it's an SP1 or SU2, it has a delta function, delta M1 plus M2. And that arises after you do this exercise. So that's a basic example of abelian gauging. So by abelian gauging, we mean that you take a UN gauge group or any flavored group, and you break up into a bunch of U1s. Okay. Now you can do something else too. I mean, you can break it into a U8 into a U5 and a U3. So those we call as non-abelian gauging. So this is like the basic example of abelian gauging. And now let me quickly draw an example of non-abelian gauging. And again, this one also leads to a well-known mirror pair. Okay. So if I start with this kind of a quiver, this has a mirror, which is 4, 2, 6. Now I take this U3 and gauge this as a U2 and a global U1. So what I get is 2, 2. Okay, on this side. Good. I've just gauged this U3 as U2 and the one global that it is. So what happens on the other side? On the other side, you have SP2 with 6 flavors. SO12 symmetry. Okay, so SO12 just indicates that there are 6 flavors under SP2. Okay. Now, you can kind of convince yourself from a counting argument that this kind of should be true. Well, I mean, firstly, this you can rigorously prove using what I just said. So if you just compute the partition function in the manner that I stated, you end up with this thing. The actual calculation is rather complicated, and it's done in our paper. But there's a nice counting argument that you can do to show that must be the case. So note that if you gauge the Higgs branch of the new theory, it decreases by 4. Okay, so you had 12 here. You still have 12. Now you have just extra minus 4. Now where will that 4 come from? It partially comes from here. Okay. So if you simply annihilate this, then this gives rise to 2 squared minus 2 degrees of freedom. Okay. So that's 2. So that's what happens if you just take away this. But there are still 2 more degrees of freedom that should come from here. And that reduces this U4 to an SP2. Okay, so the Higgs here, remember, should correspond to the Coulomb here, right? So if the Higgs branch on that side reduces by 4, Coulomb branch on this side should also reduce by 4 in dimensions. So if you take this away, then this just becomes 2. I mean, it reduces by 2 because this 2 is not there anymore. But the additional 2 comes from projecting SP4 to U4 to SP2. Right. But this you can rigorously check, and it's easy to generalize this to any SP and C with NF flavors. So what you do is you start from C at the top. So this means a TU 2nc minus 1 tail. This is mirror symmetric to 2nc, 2nc minus 2, so on and so forth, 2. So if you gauge this, NC, and what you end up here is simply SPNC with NF. Now, there are many infinite families of mirror pairs that can be generated in this way, and those include several affine D, non-affine D, then affine E, non-affine E, and so on and so forth. Also the star-shaped quivers. So it almost turns out that all the known examples of quiver theories that that are available in the literature can be pretty much generated in this way. Okay, again, I mean, none of these have Chern-Simons terms though, so that's another story. But without Chern-Simons terms, almost all the things that we know can be generated in this way. And their mirrors, if they exist, can be predicted. Lagrangian mirrors. But there's another nice thing with which I'll end that we learn by doing this. It's a well-known fact that a large number of mirrors that you obtain by simple S duality, naive S duality, are actually bad theories. So this takes us back to the good, bad, ugly definition of Gauss-Witten, which basically means that if a theory is bad, then its IR SCFT has it's not well defined. There's not a single clean point that the mirror flows to. And it's a long-standing problem to figure out if there are some good mirrors. I mean, instead of the bad mirror, if there are some good mirrors of those theories that one can construct in various ways. Now, our method basically gives you a way to construct good mirrors for a bunch of theories like that. So one example that is very well known in the literature is the example of affine D theory. This. So it's a D-type quiver with two flavors, and its naive S-dual mirror is following. P1. Okay. Now this node is bad. Okay, so this node is bad in the Gauss-Witten sense. So this does not flow to a well-defined superconformal field theory in the IR. Another way to say that is that if you observe variables like index or partition function of this theory, you'll see that it diverges. So it's not a well-defined one. So now, a long-standing question has been how to construct good mirrors of these kind of theories. Now, it quickly follows from our can I take like 2 more minutes? Is that okay?
Yeah.
Okay. So it quickly follows from our description that one can generate good mirrors for these kind of theories using this technique of gauging. So how does that work? You start with a linear quiver again. So now I'm doing it for a generic DN hat quiver. So you start with this, and this is mirror to this. So to generate the D-type quiver, I need to gauge this U1 and this U1. Then I get back here for generic angle. So once you do that, you'll see that this particular DN hat quiver that you generate is mirror symmetric to a U1 with 2 flavors and an SB1 with N flavors. This is indeed a good theory. Okay. If you compute the partition function of these guys, it's a finite quantity. So this, and this is only one example. There are several examples in our paper where we generate good mirrors for bad theories. And it could be done consistently at the level of the partition function using this gauging technique. So in addition to basically classifying your mirror symmetry of various quivers for you, this actually does this practical thing where you can generate good mirrors where there were none. Yeah.
So how can we have both a good mirror and a bad mirror? I mean, is that because it's a statement about the UV theories, 2 different UV theories, which are trying to flow to?
Say it again. Yeah. So there is another theory which has again different UV description, but flows to the same problem. There are several future directions that one needs to probe. One of them, of course, is to generalize this story to optosymplectic quivers. So far, I've only talked about unitary gauge groups and derivatives from there. But one might want to try a D-type quiver with, say, SOSP groups. Okay, that's another popular thing, a la Gaia-Lewin. But you still cannot do that using our technology. I mean, you need to make this gauging technique a little bit stronger to actually address such kind of quivers, although we believe that this could be generalized to those things. And the other thing would be to generalize these for generic n equals to 2 quivers, which also is an important problem. Okay. Thanks for your attention.
Thank you.
Bye.
Questions or comments?
Can I take gauge coupling function to 0 though? In that case?
Say it again.
If I take gauge coupling to 0 though, that is finite multiplier.
Gauge coupling to 0. So the S3 partition function is independent of gauge coupling. So it's RG independent. So there's no GM there.
But somehow by turning on the switching, you can get good mirror.
Yes, but that doesn't depend on the gauge coupling. I'm basically going to a different theory. So I'm just so that's the thing that is equivalent is the partition function. That's all that's.
So gauging will not change the partition function.
No, it changes, but it just takes you to a different theory altogether.
Oh, take different theory to IR.
Right. No. I mean, it's in the UV itself. It takes you to a different theory. Right. So here I mean, the initial theory that I started with was not mirror symmetric to the D-type theory.
But if your result is equal.
Say what?
As you gauging, basically you take the original theory to another theory, not simply gauging the original theory.
Sorry, I didn't follow.
This is gauging of the original ungauged theory. You take
Ungauged theory on the other side, yes. Exactly.
gauged theory on the other side.
Yeah, correct. So you can see in all these examples, right? I mean, so for example here, I gauged U1 and U1, and this became, from this to this. So your rank of the gauge group here was 2 plus 1 plus 1, 4. Here is 1 plus 1. So this is where the ungauging took place. And this is like the generic effect of gauging on one side of the duality. Yeah, but when you're gauging, you're actually going to a different theory. It's just that it's convenient to do that at the level of the partition function in this way. Okay. But it's to start with, it's an honest to God different theory. So if you did not know the partition function or any other convenient observable to play with, you would have to begin from scratch, like write down the Lagrangian and do all that stuff. the reason why you don't have to do that is, we know from localization that this must be true.
More questions? All right, next speaker.
Thanks.